Uh, this is the second part of Module 20, Enzymes and Vitamins. In Module 1, we discussed the enzyme regulated by three type of regulations. The first type of regulations was discussed there in the first part, esoteric enzymes and feedback control. The second part will start with the covalent modification. So let's start with the third part of the regulation of the enzyme. So the covalent modification, the activities of enzymes will depend, of course, on the formation or the cleavage of bonds on the enzyme polypeptide chain. Such dependence is called covalent modification, which can regulate the enzyme activity. It's called what? Covalent, again, modification, which in turns regulate the enzyme activity. Two examples of this regulations of the covalent modification. We have Semogenes. Semogenes are proenzymes. Some enzymes becomes active as soon as they are produced. And fold into tertiary or quaternary structures. So, in order to some enzyme will be very active, they have to have chains folded into tertiary or quaternary structure. Semogenes, also called proenzymes, are produced as inactive enzymes. That's very important, and this is inactive. We saw that before, and stored for further usage or need. And if you recall, this is insulin, correct? Insulin here is Semogen. The non-active part is called Semogen, means the proinsulin, and made of, this is chain A, has 21, correct, carbon atoms, and this one has, B has 30 carbon atoms, correct, 30 carbon atoms or 30 amino acids. Now, if you look at this proinsulin or Semogen, this is inactive because it's connected. Is connected through the disulfide bridge or disulfide bond. In order to make this Semogen activated as an insulin to release to the blood stream to control the high sugar content, then this bridge has to be broken, and the chain B is released free, and chain A is released free. So they are not connected to each other, and therefore we can't speak about active insulin. So this is part of the covalent modification. Examples. Let's look at the further examples. Enzyme inhibition. Well, it looks like the activity of non-allosteric enzymes can be inhibited by binding of specific molecules or ions, which are smaller in size, to a non-allosteric enzyme sites. These smaller ions or molecules are inhibitors, correct? Inhibitors prevent the substrate from binding to the active site of the enzyme. Let's look at this. This is a normal reaction here for the enzyme. Very nice and very normal. You have a substrate coming in, and the shape of the enzyme, this is the enzyme here, the shape is nicely done, see? And the fit of the substrate with the enzyme, see, very nice fit. See, it fits very well, and therefore reaction will produce products. The inhibition now, we have an inhibitor will compete with the substrate. The inhibitor will come, this is an inhibitor here. The inhibitor will come and take over the active sites and block them. So the substrate cannot come and react because it's excluded, because the active sites are already taken by the inhibitor. So in this case, we say inhibitor competes with the substrate overtaking the active sites. So there will be no reaction here, no products, no reaction. The second one. So here it is, no reaction. Here we have a reaction. There are two types of inhibitors: reversible and irreversible. So if we have reversible, then we will have irreversible as well. So if you look at this, this is two types of reversible. The reversible are two types: competitive and non-competitive. This is non-competitive here. Let me just, this is non-competitive, this is competitive. What's the difference between them? Well, look at this. This is the substrate coming in to react, but the inhibitor will come and take, this is the inhibitor here, come and take over the enzyme, correct? So the substrate cannot come, it goes out, so there is no reaction. Another type, the non-irreversible, reversible, but another type, they call non-competitive. You see here, non-competitive? This is the inhibitor, but does not really come and take over the whole active site. It came here in one site, not allosteric site, and with this here is forcing the active sites to be reshaped, and so that they will not fit the shape of the substrate. The substrate goes away, and there is, in this case, there is no reaction. Correct? There is no reaction. So this is this type is competitive inhibitors, correct? And this type non-competitive inhibitors. This one here, the inhibitor is here at the side, not allosteric, just any side. It's stuck in this side, attached to it, and then forcing the active side to change its shape, and the substrate cannot fit. The competitive come and take over the whole active sites. Now the good thing about this, if the inhibitor will go away, then the substrate will take over and the reaction resumes to the products. So those are not permanent. They can be removed later on. Okay, so that's very important to know. Reversible means they are not permanent. They don't stay forever. And if the condition changes, they are kicked out of their attachment to the active site or the outside sites here, and the reaction can resume. Here you can see this is the normal case. This is a normal case here, no problem, no inhibition. So very nice to see here. You can see the this one here. It fits exactly inside. So it fits the inside the active center of the enzyme. So that's normally happen. It goes to active site. It is binding to the active site. Very normal. The competitive, the inhibitor will come and take over the sites, so the substrate cannot come and fit in. That's competitive. But it's reversible, because anytime the condition changes and this inhibitor is kicked out of the active site, substrate come in and the reaction resumes. And the non-competitive inhibitor, it come and take the inhibitor this time, come and sit at the side, not inside the active site, not taking over the active site, but at the side, will push the active site to change their shape, so that the the substrate here cannot fit in, correct? So this is non-competitive inhibitors. So the non-competitive inhibitors alters the conformation of the enzyme, so active site is no longer fully functional. The irreversible inhibitors, it means it's permanent there, and this can cause a big damage for the enzyme activity. So the enzyme with the irreversible inhibitor cannot regain, so this is very important, cannot regain the enzyme activity. That's very important. Irreversible inhibitor can destroy the enzyme activity. Irreversible inhibitor forms covalent bond with the R group of an amino acid with the active sites of the enzyme, which will prevent the substrate to bind to the active sites, and therefore no reaction will happen. Inhibitors become part of the enzyme structure, and the active sites of these enzymes are blocked. Look at this. This is our enzyme here. Okay, that's irreversible inhibition. This is our substrate. Now this is the inhibitor. The inhibitor is now going in and will be, see here, it's part of, correct? It's part of the enzyme, and so the substrate cannot fit in. So there will be no reaction, and the reactivity and activity of the enzyme activity of this enzyme is permanently damaged and destroyed, permanently destroyed. Here, just to give you an example of the irreversible inhibitors, that's the active site. This inhibitor will come and fit inside the active site, or here, see here, it goes in, and it will become all this now one enzyme, including the inhibitor. So you see, a reversible inhibitor binds permanently to the active site, so the substrate can't bind. The substrate will come here, wants to come in, it can't go in, correct? And the enzyme function is permanently disabled. Here is just to show us some of the inhibitors, and they are really poisons, listed here. Arsenate, this is the structure of it, and it can substitute for the phosphate. That's what they do for the enzymes. So iodoacetate, this is the structure of it. It binds to cysteine thiol group, CH thiol group, and the diisopropyl fluorophosphate, and this is the structure of it. And this binds to the serine OH group. So they bind to the groups. You can see to the polar groups, like thiol OH group, correct? And therefore you'll see that they are really poison, and they're destroying they will be part of the enzyme, and the enzyme cannot get rid of them, and the enzyme is said to be deactivated or destroyed. Here's another compound, the peptides, organophosphate nerve gas, and the peptides here. Okay, they can cause paralysis. They bind to the serine OH group. The mercuric salt and arsenic salt bind to the thiol groups, as we said. They can cause widespread cellular damage. Cyanide can bind to the cytochrome oxidase, can cause suffocation and death. Digidoxine can bind to sodium and potassium ATPase, inhibit sodium ion migration. So all those are highly toxic compounds or ions, and can cause the enzyme to be destroyed. There will be permanent, irreversible permanent inhibition. Now let's look at the enzymes and cofactors and vitamins. Enzymes are active, as we said, when the polypeptide chains are folded. This is very important. When the enzymes are active, they are always active if the polypeptide chains are folded. Some enzymes need cofactors to catalyze specific reactions. The cofactors are metal ions or small molecules, and a small amount of these cofactors are needed to facilitate the enzyme catalysis reaction. Some example of those cofactors, also called sometimes co-enzymes. So those cofactors, metal ions such as copper, iron, zinc, magnesium, manganese, and nickel, for example, ions. Or the second type of these cofactors, called coenzymes as well, organic molecules, which include fat-soluble vitamins as well as water-soluble vitamins. And they are, as I said, they are said to be coenzyme, said to coenzymes. So now let's look at this here. This picture here gives us just the idea about those cofactors. Cofactors is very important. They are not protein. They are non-protein. So they are not part of the amino acids chain. They are not produced in the body but taken as supplemental, correct? So, and those cofactors can be two types. We have organic molecules called coenzymes, or inorganic ions such as calcium, zinc, magnesium, and so on. So two types. They are non-protein. They are not part of the chain of the amino acids, but they are not produced in the body in some way, but they are taken as supplemental. Cofactors may permanently attach, and this is very important, to the enzyme, and in this case called prostatic groups, or can be temporarily attached to the coenzymes, which detach after the reaction, and may participate with another enzyme in another reactions. So here we have, this is just the active side. This is an enzyme, protein only example. This is only protein. Now we added the cofactor here. We have prostatic group here, and those prostatic group, if we have permanent attachment of the inorganic ions or the coenzymes, organic molecules. So this is permanent attachment. So in this case, this permanent attachment, and in this case, just temporary one. So they are really attached, coenzymes attached to the enzyme. And this is just an example of the reaction that's really supporting this idea. So metal ions cofactors. The metal ions cofactors here is an example, zinc. Zinc is in tetrahedral. If you look at the zinc, it's tetrahedral shape. Here's the zinc, tetrahedral, and is connected to 3 rings of the imidazole, 5-member ring, and zinc is here, and the H2O is in the top. So this is a tetrahedral arrangement of zinc, and is needed. This one here is this one here is called carbonic anhydrase. Carbonic what? Carbonic anhydrase. This is carbonic anhydrase, and it utilizes zinc ion in the presence of active site cleft. So you have in the active site, you have active site this structure. This is the enzyme here, carbonic anhydrase, utilizes zinc as cofactor. So here, this is nickel 1 and nickel 2 in this huge enzyme, and you can see there's a lot of folded chain of amino acids all over the place, and zinc is in between here, two zincs, not zinc, two nickel atoms, sorry, two nickel atoms is there, and therefore this enzyme is utilizing two nickel ions. And here just a table show you what type of enzyme and what cofactors is cofactor is used, metal ion is used. So for example, copper 2, I'm not talking all this, but just selected ones. Copper 2 is enzyme is cytochrome oxidase, iron 2 and iron 3, cytochrome chrome oxidase, catalase, peroxidase. So, and if I look at nickel, urase, okay, from urea, okay, and zinc 2 plus, that's we just we saw this. There's the enzyme called what? Carbonic anhydrase. Just we saw it a couple minutes ago, or alcohol dehydrogenase, or carboxypeptidase, A and B. So all those ions you can see are used for different enzymes in a very specific type of reactions. Organic molecules, which include fat-soluble as well as water-soluble vitamins, coenzymes. Vitamins are considered as a cofactor, and they are also called coenzymes. They are not produced in the human body, as we said, but they are very essential in a small amount for the human health and growth. They are not by all means amino acids. They are not amino acids, correct? That's very important to know. There are two types of vitamins: water-soluble vitamins, coenzymes, and fat-soluble or water-insoluble vitamins. The water-soluble vitamins have the polar group, such as the hydroxide groups here, or the carboxylate group here, carboxylic group. They are easily destroyed by higher temperature, light, radiation. And they are also easily destroyed in presence of oxygen. Oxygen can destroy them as well. Example of water-soluble vitamins are B1, thiamine, B2, riboflavin, and we'll come in a minute. In the next slides, we'll see a couple of those water-soluble vitamins. Okay, let's see now maybe. Yes, they are here. All those are water-soluble. Vitamin B1, B2, B3, B5, B6, B7, B9, B12, and vitamin C. Don't forget vitamin C, which is ascorbic acid, correct? Vitamin C is ascorbic acid. And you see the water-soluble vitamins, and then you see the precursor of this, from where they are coming. So B7 called the name, that's the name of them. B7 called biotin, B9 is folate, and vitamin C ascorbic acid, and B1 thiamine. And this is just type of fruits they are inside. They are found plenty in the fruit. Now, what's happened if we have deficiencies in those water-soluble vitamins, such as vitamin C? Well, it turns out to have a very bad sequence for having low in those water-soluble vitamins. If we are lacking them, then we'll have a lot of health problems. So for vitamin C, then we'll have problems. We'll get slowed hearing, increased susceptibility to disease. Let's take niacin, for example. Niacin, if we have a little bit of niacin, we have deficiencies in lysine, then we have a problem in the loss of appetite, weight, inflamed gums, and diarrhea. So, and you can look at all this folic acid. Let's take folic acid, very famous. If we don't have that much folic acid present in the body, then we will have problem with the hypoplasia of bones, marrow, and we'll have anemia as well. Vitamin B12, that's also very famous. We have macrocytic anemia. Biotin, if we have biotin here, missing a lot of then we'll have poor hair, dry skin, and diarrhea. So those are very important one, and they are taking supplemental naturally. The most of the fruit they have them. This is just the structure, and we don't have to memorize them, but at least you get the idea when I say vitamin B1. Okay, so B1, how does the structure look like? And this is B1 vitamin, thiamine. This is B2 vitamin. That's not amino acid, although nitrogen is there. See, plenty of nitrogen. This is nitrogen, 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 correct? But they are not, correct? They are not amino acid by all means. So here it is, then it goes B3. But you can see this is an imide. This is typical imide here. And this is B5. Again, nitrogen is there. And then B6, nitrogen is there as well. So those are just an example of their structure. We don't have to memorize the structure, but at least to get the idea how they look like. Let's look at maybe folic acid. This is folic acid now. See here? This is folic acid, okay, B9. And this is the complex one, B12, and it uses cobalt here. If you look at this, cobalt, again, in tetrahedral arrangement, a shape, and the cobalt sit inside, you know, and they inside the structure, okay, and you can see this is B12. It's very complex, very large complex molecule utilizing cofactor cobalt ion. Water insoluble vitamins. The water insoluble vitamins, they are also called fat soluble vitamins. Example of them: vitamin A, D, E, correct, and K, and E here, A, D, E, K. So the fat soluble vitamins are not considered coenzymes. They are not considered coenzymes, but they are very important in health and growth of human body. They have important functions in vision, as vitamin A, formation of bones, vitamin D, blood clotting, vitamin K, correct, prevention and clothing prevention and prevention from oxidation. Fat-soluble vitamins can absorb free radicals coming from the oxidation inside our bodies, and those are hydroxy free radicals, nitrogen oxides free radicals, oxygen free radicals. Those, because processed through the oxidation, can produce free radicals, and they will be easily absorbed by fat soluble vitamins, correct? And those free radicals can cause the cell to mutate, and the tumor will be produced, and later on these tumors can develop cancer disease. Here are those all these veggies full with fat soluble or water insoluble vitamins: A, D, and E, and K. A, D, E, K. 4 of them. So let's look at the vitamin A. Carotene, correct? And here just the function here, vitamin A, we said, maintenance of skin, hair, correct? Helps people with their, to see very well, good for the eyes, the dim, and the teeth growth. Vitamin D, as I said, for the bones. Vitamin E, protect the blood cell from clothing. And the K cause blood clothing as well. So vitamin E is essential fatty acid. It's not a fatty acid. but it's protect the fatty acids from being harmed or destructed in our body. So those are 4 insoluble vitamins, and they are really very, very important. They have very important functions, and they are found in the vegetables. Here are how they look like. This is vitamin A, and those double bonds here, if you look at this, double bonds here, double bonds here, double bonds here, another double bond here, those are the ones who are absorbing the free radicals. So this is the vitamin A, part of the visual, good for the eyes, protecting the eyes and the eyesight. And the same time is antioxidant, because of the too many double bonds can absorb any free radical. Vitamin E is antioxidant. That's the function of it. It's antioxidant and prevent any blood clotting as well. And it has double bonds as well. As you can see, it has a double bond, although in aromatic, but it has still a double bonds here. And the vitamin D is good for the bones, calcium metabolism, and the bone growth. And it has, again, this the secret of the absorbing the free radicals here. This double bond here, and there's another one here, there's another one here. So this is for the bones, okay, calcium metabolism and bone growth. And vitamin K is good for the blood clotting. It's not allow any clots of the blood. So, and again is considered antioxidant, because you have plenty of double bonds all over the places here. They can absorb, and here the ring as well. They can absorb any free radicals. Let's go and look at the vitamin A precursor. Vitamin A precursor is beta carotene. See how many? Too many double bonds here. And here's another one. This is very good antioxidants. Although vitamin A is good for the eyesight, but is a very excellent antioxidant because it has multiple double bonds. And it's the beta carotene is the precursor to make the vitamin A. And the ergosterol is the precursor to make vitamin D, and vitamin D is for the calcium metabolism and for the bone growth, as well as we have a double bonds here, and we have a double bonds here, and we have a double bonds here. So it's antioxidant as well. Thank you very much.